filmando.
Okay, so hi everyone, welcome back to a new edition of our seminar. Today I have the pleasure of introducing Sebastián Zaninovich from Universidad de Buenos Aires. He's a PhD student there of PATU, and he's going to be talking to us about asymptotic behavior of path distances in the presence of paths.
Thank you, Santi. Well, hello to everyone. I'm going to talk about path distances. This is a work that we did with PATU when I was doing my master thesis. And now we are doing it, we are finishing it with Alejandro Wences from LAS in Cruz and with Steven Lam in California. Okay. Well, first I want to talk about first passage percolation and some results that there are there. Well, first passage percolation, we have the grid ZD, and to each edge, no, it is the 0, and to each edge we put a random variable. Okay, tau sub e. Okay, and if we have a path here from 0 to some point x, the cost of this path is we sum over all the random variables of each edge. Okay. Well, and we define the passage time between 0 and x as 0x is the infimum. Well, is this? Is the infimum of over all the costs from the path between x and y. Okay. Well, two questions that are very relevant in this topic is the behavior of t of xy when the difference between x and y tends to infinity, and how regular is t with respect to tau, okay, to respect to the random variables, but to the distributions. Okay. Well, this is a very well-known result that if the random variables are good, if we have this hypothesis, then the distance from 0 to n times e1, this is the first canonical vector, is of order n, and this converges to a time constant, mu, and the convergence is almost surely and in L1. Okay. Well, and then we have this result that is about the regularity. If the tau n are good random variables, and tau n converges in distribution to tau, then the mu n is the time constant of the random variable tau n. Well, mu n converges to mu. Okay, that is, mu is the time constant of tau. Okay, we're good. Well, something that is easy to prove is that if we have two random variables, tau and tau prime, and one is dominated stochastically by the other, then the time constants are dominated in the same way. Okay. But something that is not so easy is when we have a strictly inequality here. Okay. There is a paper, and you have some hypotheses for proving a strict inequality here, but it's not an easy work. Okay. Well, now I'm going to talk about the Howard-Newman model that is that is a first passage percolation, but in the Euclidean plane. Okay. The model is as follows. You sample a Poisson process in Rn, for us n will be 2. For a path tau, for example, imagine this is 0. We have this path. And we have Q1, Q2, Q3, and X. Okay. And the cost of this path will be the sum of these differences if you want, 0 is Q0 and X is Q4 here. Now, the cost of the path will be the differences, these distances, but to the power of alpha. And alpha will be a parameter that is greater than 1. Okay. What is this doing? Well, okay. Now you define the passage time between 2 points, 0 and X, as the infimum of all the gamma, such that gamma 0 and X. Okay. It's the infimum between all the paths that connect 0 to X. Okay. Well, and what is doing this alpha? What is this? This alpha is penalizing long jumps. Okay. Because you are putting an infimum here, and if you have a long jump, imagine alpha is 2, then the cost will be very big. Okay. And if the jump is very small, this will be very small as well. Okay. So the idea is that the distance will be achieved by a path that has a very little jumps. Okay. Well, what is known in this model? Well, we have a linear growth, no, and we have a time constant as before that depends on alpha and d. Okay. Well, a quantity that I'm going to define here is the quantity of points that the geodesic have. Okay? And I will denote as k sub x. Okay. Well, k sub x in this model is not so hard to compute or to estimate, and we have this like if imagine a sub n is n, like the geodesic of from 0 to x, we have something like n points. Okay. Well, and now this is the model that we are working on with Patu, Alejandro, and Steve, and it's like this. Okay, this is not very formal, but the idea is the following: we have the Poisson process in R2. And now to every point, we are adding a random variable in an independent way and with the same distribution. Okay, and we are going to call this random vector the noise. Okay, and the noise can go outside the plane. Okay. Well, this is what is this definition. We have a Q, the Poisson process, and to each point we add a random vector. Again, this is not the most formal way to define this, but for the sake of understanding this is okay.
So the point process is in the
lower
dimensional space.
Yeah, you have RD, that is the first Poisson process, and then to to each point in this plane, for example, these two here, you add a random noise, random vector.
And the noise is just in the other, in the orthogonal?
No, I'm going to talk about that later, but first, for now, it's going to be. But the idea is the non-orthogonal component is going to die because of the homogeneous of the Poisson process. Okay, so it's the same, will be the same. Well, now as well we define the Fermat this distance between points, and that is the same as the one before, but now the points are in RD. Okay, the same. Okay. Well, this is what I was saying. That if we have this process that is going to be xz, we set the distribution of the random variable, then then xz will be a Poisson point process in RD with R. RD is R3 here in the drawing. Okay. And which is the distribution is this. In the first, in the floor, for example, here in R2 is going to have the Lebesgue measure, and in the orthogonal component we'll have the projection. Okay, it's like the non-orthogonal component is going to die. Okay. Okay. Yeah. Well. And then we have this result.
What? I don't understand what you mean by dying.
Okay, because in general, yes, it's canceling. Okay, if you have a Poisson process in R2, for example, and to each point you add a random vector in R2, all with the same distribution and in an independent way, the result is going to be a Poisson process. Okay. Well, this is the analogous. So you add you have a Poisson process, you add a random vector, and the non-orthogonal component is like this. Okay. So the only thing that survives is the orthogonal. It's okay. Okay. Well. And as always, we have this theorem that is the linear growth of the model. Now the time constant is going to depend on the distribution will depend on sets, okay, on the distribution at least. And the conversion is almost sure. Something like that is easy to prove is this monotonicity, okay? Like if you add a noise, the time constant with noise will be bigger than with no noise, okay? This is because we are going to see this drawing like this, okay? Like you have the Poisson process, you add the noise, now we can think that is orthogonal. No, we have this. So the path with the noise are going to be like this. Okay. And with no noise will be this. Okay. So the noisy path will be bigger by Pythagoras theorem. So this is just a remark. Well, the first theorem we have is this double limit. That is if the noise tends to 0 in distribution, then this double limit will tend to the non-noisy constant. Okay. Like now, in each step we are changing the model because we are changing the noise. Okay. So in the distance between 0 and the point n, we will put a noise Zn. And the Zn are going to tend to 0. Okay, so if the noise goes to 0, then we converge to the non-noisy constant. Okay. Well, this is not you can't deduce this from this. Is that we have continuity on the time constants. Like if the noise goes to 0, then the time constant of with noise tends or goes to the non-noisy time constant. Okay. Well, sorry, and this is the theorem that I stated before from Cox that in first passage percolation you have continuity on the random variables. Okay, the same happens here. Well, and now we ask ourselves about non-trivial constants. No, because it is true that if you have a noise, the time constant with a noise will be bigger than the non-noisy one. Okay, but when do we have this? Well, this was not obvious. It is not obvious because, for example, there are noises that have a trivial time constant. For example, if the noise is constant. Now, if this is a deterministic vector, what are you doing here is just translating the plane. Okay, so the time constant will be the same. But well, we proved this theorem that if the random noise has admit a density G, and the density G satisfies this property, then the noisy time constant will be strictly bigger than the non-noisy one. Okay, and what is this? This we have I have an intuition from this. Mu RD is the non-noisy time constant in dimension d, and this is the non-noisy constant in dimension minus d. Okay. Well, what is this? Well, this is
alpha.
Sorry.
What is alpha?
Alpha is,
alpha is
the one of the definition, the one of the shams.
Yeah.
Okay. Well, what is this saying? Like, for example, if we have this distribution, the idea is that it's bounded by a constant. This is a constant, and the idea there is that if the constant is not so big, the mass of the distribution, if here is zero, then the mass will have to go far away from 0. Okay, so you will have a mass here and here, far away from 0, and then the noise will have a positive probability of going far away from 0. So the noise will be like here, here, here. Okay, so you will have to do long jumps. Okay, this is a little intuition. What else do we have? Well, and we conjecture that if this is what I was able to prove, and this is what I think is true. Okay, that if the noise, well, here I put d minus d because we can think that the noise is orthogonal. Okay, so, but it's the same. You can put here d. Well, if the noise is non-deterministic, then the noisy constant will be bigger than the non-noisy one. Okay. Well, now
So just a stupid question. If you just have, let's say, it takes just two values, for example.
yes.
Can you prove it?
No. My first try was to prove it in the Bernoulli case, and it's very difficult because you don't know what the optimal path is doing. So, but here I could, in this case, I could couple it with another Poisson process, and there I know that constant is different, blah, blah, blah. But no, the Bernoulli case is hard as well. Well, now to manifolds. Okay. The idea is the same, but now your points it's not the distance between 0 and a point x, and x is going to infinity. Now your 2 points are going to be static, like they are not going to move, and what you are going to do is to sample more points. Okay, so we have a manifold. And 2 points, x and y. And as before, we sample some points, endpoints, no, with a difference, with a density f. Okay. Maybe there is a place here with a lot of density. Here no. Okay. And we define the same distance as before. Okay? The distance between x and y is you compute the cost of a path as before. The T of gamma is going to be the sum like this and like this. The sum of the jumps to the alpha and use okay. Well, and then you define the distance as the infimum. Well, there is a theorem from Fatu, Matt Jonker, and Paco Sapienza that states the following: that if you define dxn as this infimum, the distance converges under a good risk element. Okay. This risk element may be a little I don't know, non-intuitive, but you can do some heuristic computation, and this is the risk element that is correct. Okay. And well, under a good risk element, the distance converges to mu. That mu is the non-noisy constant of what I was talking before, times this distance, df x, y, and here parameter alpha minus 1 over d. And what is this distance? Is this. Okay. Now you have the density, and now you are going to make the infimum, but over all rectificable path. Okay, and over this integral. So see that if you have places with a lot of density, this will be very small. Okay, so the infimum would like to go to these places. Okay, because if the density is very big, 1 over f is very small, and then you are taking the infimum. Okay, so in the microscopic way, in the microscopic case with the random points, this is saying that the geodesic will want to go to places with a lot of points. Okay, and this is true because you want to do short jumps. So the geodesic will want to go here, 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 here. Okay. Well. And this the order of the risk element, we are going to call it beta. Okay. Well, it is not it is not hard to prove that the quantity of points in the optimal path is going to be of order n to the 1 over d. Okay, in an open connected bounded set. Okay, like if the manifold has the same dimension as the Euclidean space, ambient space. Okay. Well, but when we have a manifold, this is very hard to compute, to make some computations, and so we have a not so good order, and we have this. And this is bigger than this. Okay, so this is not optimal, but it is the only order that we have that we could compute. Okay, but we conjecture that the order is this. Well,
But doesn't depend on alpha.
no, only the dimension. Only dimension. Okay. Well, the alpha is always fixed in general. This constant will depend on alpha, but not this. Well, and as always, we define the noisy case as we have the random points in the manifold here, and we add a noise, no? That is going outside the manifold. Now, they are not orthogonal, no? The manifold, it can be, oops, like this, like this, like, okay. And we define the distance as always. Okay. Well, what we could prove is the following: that if the noise tends to zero very fast, when very fast is like this, then we have the convergence of the distance under the good risk element to mu times the Fermat distance. Okay, this is the one, but the non-noisy one. No, okay, this is the one of the integral. Okay. Well, the conjecture is this: that if the noise tends to zero in this way, like rescaled by n to the 1 over d, then you will have the conversions you want. Okay. Notice that this is very this is faster than this. Okay. Well, but we could prove this statement when the manifold is an open set. Okay. And the noise is orthogonal. No, for example, well, when it's an open set of a lower dimension. Okay. Like if we are in R3, then we can have an open set of R2 and the noise orthogonal. Okay. Why we could prove this? Because if we make zoom in here, it's like the Euclidean model. Okay. So, and there we have good results. Well, we really think that this is the good order of conversions, because we could prove it in this case when it's an open set of a lower dimension, blah blah blah, and if the convergence doesn't goes to zero, for example, goes to a random vector, no, this is always in distribution, then we could prove that there exists a manifold, that the manifold is the square, and well, the density is 1, that you don't converge, okay? Because the limit of this is bigger than this. And now this is the noisy time constant, okay? With the one that was bigger than the non-noisy one. So this will never converge to mu times this, okay? Well, I think that this is everything. Thank you. And now, sorry.
Questions?
But when I was just thinking, you are always doing this on RD, and then you're adding another, but could you do it on a manifold or some nice story?
No, we did the thing in the manifold, okay? These theorems. For example, this theorem is in a manifold. You sample, you add the noise, and then if the noise goes to zero very fast, then you have the conversions. No, this is in the manifold.
Thank you. Sorry.
Okay.
I guess that I remember Fatu talking about the earlier works.
Yeah.
And they have to do with, it was something like machine learning.
Yeah.
So I guess that's the motivation for the noise?
Yeah, because in the real world, the point doesn't go in, they have noise, okay? So that was the motivation. But I don't know nothing about machine learning and that kind of stuff. I just do the math.
So, I don't know. So why? Maybe I'm missing something, but say you take alpha equals 2. Just so that
What? Sorry?
you take alpha to be 2.
Say.
And you do this Bernoulli thing that Avelio was, where you say you add either 0 in one direction
Yeah.
or 1, or -1 or 1.
Yeah.
Why can't you prove that?
That is bigger.
Yes.
I don't know. You have to prove that all the path.
If you give me the optimal,
Yeah, so if you get the optimal one, that one increases. The question is how many paths are epsilon optimal? Yes.
Well,
For the Bernoulli story, that's the question, no? Like if you have the optimal one without the noise,
yeah.
this one will increase.
Yeah, but
And then the question is how many epsilon optimal paths are?
yeah, because in the Bernoulli case, for example, you will have
Meaning that instead of going to mu, you go to mu plus epsilon.
for example, in the now you put the half of the points will go up and the other half will be on the plane. Okay. And if you take the optimal path in the floor with no noise, and then you go to you see it with noise, that will be bigger. But you have to prove that all paths.
No, it's not all paths that you have to prove they are
That's-
bigger. You have to prove just the paths that are almost optimal.
if I take the optimal path with noise,
Yeah.
and then I project it, does that give me a bound on the, unless I'm getting the inequalities wrong?
Yeah, you're getting.
I am getting the-
You have
yeah.
to get all the paths. So you're always, so that one will be worse, but there may be some path that it's not the geodesic, but it's almost the geodesic. And this one doesn't move. So the geodesic one will move.
On which side? I'm not sure.
So it is going, so you're always going to go up. So every path is
No.
going to have its distance to go up, but there may be some paths that they do not move the distance. No, I'm wrong. So there's
No,
some,
here when I'm talking, I
they're
can't
not
think.
gonna
Sorry.
They're not gonna move because it's.
no, not all, because if you have one path where all of them got 1 in your Bernoulli. So there is at least one path where all of them got 1. So then the question is that path close to being optimal? So you have to count how many epsilon optimal paths you have, and you have to make some entropic argument there. The intuition is it should work, but still you have to count something.
Great.
Can you put the last slide on the one about the
Can you slide?
no not so last. Casi no not that one. Yeah. ¿Cuántos caminos óptimos hay? Okay. So, but can't you have you tried decomposing like the manifold into something which looks like an open set?
For
Right, because
for the conjecture.
yeah, both points which are kind of close, the manifold looks locally like an open set.
Yeah, but that doesn't work because I think the idea is no, you have you have XY. No, you decompose and in open set the charts, blah blah blah. But the distance between this and this, you don't know where when you when this chart goes to the Euclidean space, okay, you don't know what you are doing, like because the infimum is over this, okay.
Okay.
Now we tried, but okay, the proof in the manifold we of course do these kind of things, but we have a lot of problems.
Well, but this gives you like that for points which are close, then it should be true, right? Because they're on the same chart somehow. If X, Y are on the
Yeah.
same chart, then
Yeah, I think that's true. I have to think it a little bit more, but
well, maybe not, okay, but because they could, the path could go out of the chart, but okay, maybe.
okay. Yeah, no, I see. I forgot to do the proof of the theorem, but
You still have time.
I have. Do you want to see the proof of I think the Euclidean space, the Euclidean case is better. Like, sorry, I didn't have them on the slide because I thought I was going to do it in the whiteboard, but I forgot. Right. This one, the one that the double limit tends to the non-noisy one. The idea is easy. You have some technical things, but the main idea is the following: the noisy distance is no, we want to see the geodesic path. Okay, so you have okay. Well, this is not it's not the optimal path for this. It's the optimal path with no noise. Okay, so you have the here you have the noise, and you take the optimal path between 0 and a point x before putting the noise. Okay, so when you see the path with noise, that will be a upper bound for for this, because this was the inflow overall path. Well, but now you split the thing in the points, in the Q points and the noise, so you have this. Okay, and then you power all to the alpha. And here you do to the 1 over alpha, sorry, because you want to do a triangular inequality. Okay? Well, and you do it, and the thing is like this. Alpha over 1 over alpha plus x. Okay. And this Qi was the optimal path with the non-noisy case. Okay, so this is equal to T sub n plus this noise. Okay. So well, you have to bound this in some way. Like, well, if the random variables are bounded, then it is easy, okay? Because this is bounded, blah, boom. Because, sorry, no, this is Tn set n, you have to divide by n for taking all limit. So you divide all by n inside the 1 over alpha. Here. Here. Okay. The optimal path has endpoints, so this is more or less like n, and you have like a law of large number here, but the distribution of this tends to 0. Okay. And well, making some computations and blah blah blah, as always, you can this tends to 0. Well, this tends to mu. And this is, so this, the lim sub of the n set n over n, if you want to the 1 over alpha, is you have this bound. Okay, and now powering to the alpha, you conclude the proof. Okay, because this was bigger than the lim sub of the n over n. Okay. That, and this is mu to the power 1 of. And okay, this is the proof. Nice, okay. Well, that's all.
One question, do you know something about the intersection between the geodesic without noise and the geodesic with noise? Like how close they are they?
No, no, we don't know nothing about that. Why?
No, it was just.
Okay.
What's the question? So there is nothing.
Nothing that we know. Okay, we didn't ask.
So
ourselves.
probably in this one, it's telling you that somehow it is continue. I mean, like somehow your geodesic is converging to the other one, or not directly, like your argument here.
Okay. No, the argument here is it's like this, but you don't put the n here. Okay. And then this converges to. No, I don't remember the.
Yeah, and in the not noisy case, do you have some kind of, even in the not noisy case, so do you have some kind of converging of geodesics, like geodesics from different points they tend to merge, or things like that?
Yeah, there are a lot of results there. The non-noisy case is not. The Euclidean non-noisy case is from Howard-Newman, and they have a lot of results of geodesic. They love them. For example, the geodesic from 2 points between 2 points is very close to the line between the points. Okay, if you see the things under a good risk element.
And if you take if you leave the line, do you know how that always the distance?
If you leave the line?
Yes, so if you go a distance epsilon from the line, then the distance always, the mu always increases. Like if you take paths that are not allowed to go across the line or something like that.
No, I don't know. I don't think. No, I don't know. Maybe they have something. Okay, I will reread the paper.
Thank you.
No, you're welcome.
Any more questions? Well, not then.
Ah,
Again?
Oh, Vamos a
Ok,
jugar
now.
con una pregunta de verdad.
No. Ya,
Ahora
no saldría.
ahora que el maestro.
No, pero yo creo que lo que sí, yo creo que este tipo de cosas es lo que te demuestra que si tenías una Bernoulli